Okay, let's take a quick look at an example of how to actually use this equation to answer a real question. So this one comes out of your textbook. It says that the rate constant for first order decomposition of this molecule, cyclobutane, at this temperature is this. So that's the rate at which it's decomposing. Here's the balanced reaction. And we're being asked how long it will take for 80% of a sample of this molecule to actually decompose. We know it's first order, so I just wrote up the expression that we've been dealing with for this whole video. So the first thing to really interpret is, what does this mean? How long will it take for 80% of the sample to decompose? And it's nice to say this out loud or write it out. So what they're actually saying is if 80% of the initial concentration, right, that's what this knot is for. So if 80% of that decomposes, then what's another way that we could write the actual concentration of C4H8? Well, that's the same as saying, the current concentration of C4H8, not the initial, but the current, has to be 20% of whatever we started with, which is the same as 0.2, because we have 20% left. If 80% is decomposed of the initial, that means that what we're at now, which is marked by this variable, that must be 20% of the original. So that's the equality that we could write here. So now can we take that equality and pop it back into the generic integrated rate law for first order reaction to then figure out what we're being asked, which is how long, or t, does this happen for? And we're given k in this equation, or so I'm just going to write this out explicitly so you can see it and you can review this and make sure you understand it completely. So all I'm doing is rewriting the normal integrated rate law expression, but I'm doing it in terms of the actual molecule here. So C4H8, this is the same as A in all of the generic examples we've done before. So now I'm just rewriting it like this. So here's the concentration of C4H8. Here's the initial concentration of C4H8. Now we have this equality that we can. So before substituting, just a quick rearrangement. We've done this a bunch of times, so I'm just going to take this term, subtract it over, which is the same as dividing with log rules. So we get something like this. Now let's substitute this 0.2 C4H8 naught into C4H8 and see what we get. So that looks like this. Now we have 0.2 C4H8 naught, which came from this section, this green line coming over here, divided by C4H8 naught equals minus KT. That's convenient because now we have two like terms. Those go away. This simplifies to natural log of 0.2 is equal to minus KT. So we can finish this up. Okay, 2 steps in one here. Now I'm taking and dividing the k here into the log 0.2, and I'm doing that as a negative, so I get rid of that minus k. That's going to leave me with t. That's supposed to be a t here. And at the same time, I'm substituting the actual value for k, which came from the problem, 9.2 times 10 to the minus 3, and I'm including the units just to keep track of the units. So if I punch that into the calculator, I get a value of 174.9, and I'm including seconds here because in this expression, natural log 0.2 does not have units. This rate constant has units of inverse seconds, 1 over seconds. So when we solve this for t, we're going to be in units of seconds. It says 4 sig figs. Let's be really thoughtful in Chem 108 about how many sig figs we actually know. So if we go back to our actual question, let's see, what did we actually know? Well, we were given this value. I had 3 sig figs. We used it. We didn't use temperature. We did use this rate constant, 9.2 times 10 to the minus 3. That only has 2 sig figs. That's shown here. That means this answer can only have 2 sig figs. So the best way to represent this is with scientific notation, which would be 1.7 times 10 squared seconds. So we just got done using an integrated rate law for a first order reaction to compute what the concentration of a species is after some duration of time. We needed the rate constant for that. But before we can ever do anything like that, we would have to know whether or not the reaction is actually first order based on the actual experimental data. And so this is real experimental data. We have time, and that at these 5 different time points in hours, so here's time 0, so let's just say there's time 0, and this then would be our H2O2 naught, that's the initial concentration, started at 1 molar, and then we see a decrease. How do we know if this is first order? How do we actually know that? Well, we need to do this graphically, so let me show you how to do that in Excel, because you're going to do that a lot in this class. So of course, the first thing to do is open a spreadsheet computation software like Excel. I would recommend using the actual desktop version because it has all utilities. Don't use the online version, nor should you use Google Sheets. It doesn't have near the power utility that Excel does. So I just took these data, popped them into here. Make sure you add units anytime you're making plots. Remember, we're trying to determine whether these experimental data fit a first order reaction for H2O2, and we know that it should behave in the form of this expression, right? We know that it should decrease in this particular way. We also understand that this form is graphically related through the equation of a straight line, y equals mx plus b. So how do we plot this to see if it looks like a straight line? Because if it's first order, it should be a straight line. That's our diagnostic. So could we simply take time and make a graph of these two variables? Well, that's not what's being represented in the actual expression, right? On our y-axis, we want the natural log of the concentration of the species. We have just the concentration, not the natural log. And then on our x-axis, x here is t, we would just need the time. So we don't need to do anything to time, but we need to transform or take the natural log of the concentration first. First thing then is just to make a new column heading, which is going to be the natural log of this concentration. That's really easy to do in Excel. So anytime I want to do a computation, I start with equals. And then I'm going to put the function that I want to do. So you can look this up online if you don't know. If you do it a lot, then you just know it. And that conveniently is just ln for natural log. It tells you that that function returns the natural logarithm of a number. And so we need to put a parenthesis for what we want to take the natural log of. In this case, I want to take the natural log of that particular cell. I'm going to close the parentheses, click enter, and that is going to return my value. The great benefit of spreadsheet computations is now I can just drag this list down by holding that bottom corner, and that is going to automatically, you can see, populate and compute based on the adjacent value that it's calling upon. So now we have this in the form that we need. Now we need to make a plot of this natural log of H2O2 versus time, and that should tell us whether or not this is a linear first order reaction. So to make a plot, if it's been a little while, typically you're in this home tab, click the insert tab, go all the way over here to charts, and then click this scatter chart that looks like that. And I'm going to now click this chart, go up here to select data, and I am going to get this dialog box. I am going to remove both of these because they are not what I want to plot. And I'm going to add a new entry. That's going to give me this new box. And I'm going to click this arrow button under series X values. I'm going to use that to highlight what I want on my x-axis. I want all of those time values. I will push the down arrow. That'll allow me to populate now the series Y values, which we computed as the natural log there. Now I will click OK. I don't really care about a series name right now. I'll click OK again, and I'm left with a plot that looks like. So let's add some axes to this because plots are useless without them. So I'll click axis title. I'll double click over here and I'll say that's natural log, not that, of the concentration of H2O2. And down here I have time, and I have that in units of hours. Cool. So what was the objective of this work? Well, we wanted to know whether or not these data that we collected for this reaction suggested that the reaction was actually first order in H2O2. If that were to be true, it would need to abide by this reaction expression, the integrated rate law, which would indicate that when you make a plot of a natural log of the concentration of something versus time, it should be a nice straight line. If it's not a straight line, that indicates it's not first order. It's a different order. What do we have here? This looks like a wonderful, perfectly straight line, and I can actually fit this line to figure out what K and RA naught are by doing a linear regression, or what's known as adding a trend line. So I'll go down here to chart elements, add a trend line. I'm going to click this over button, and I'm going to go down to more options. that more options is going to give me some stuff over here. I'm going to click these little bars here under trend line options. I want a linear trend line because I'm plotting this to see if it is linear. And then down here, I can display the equation on the chart. That's really useful. I'm also going to display our squared value on the chart. That yields these expressions here. I'm going to just make this a little bit bigger. We'll say pop that up so you can see it. What that tells me is that this line is perfectly straight. The r-squared value is a measure of straightness, how well those points fit the trend line. A value of 1 is perfect. Any value less than 1 is a percentage of that perfection. So 1 is perfect, so this is a straight line for sure. And we now have an expression in the form of y equals mx plus b for this line. And we do not have any y-intercept. We have that intercepting through 0 here, which means that the natural log of A naught, or H2O2 naught, is going to be, the natural log of that is 0, which means that the original concentration was 1, which is exactly what we have. We already knew this. More importantly, if we wanted to figure out what K is, it's going to be the negative of this slope. So this slope is already negative, so our K would be 0.1155 because the negatives would cancel. So I'll move this into a space where I can write, which is a little bit easier here. So as I mentioned, this term is the same as B. B here is got to be 0 because it doesn't exist. So that means the natural log of A naught has got to be 0, which means that A naught is 1 if we did the exponent on both sides, which turned out to be the same. It's 1 molar, and we knew that already, but if we didn't, we just figured it out. Similarly, we know that our slope here is minus 0.1155, and slope is equal to minus k. So m is equal to minus k, which is equal to minus 0.1155. So that means k is equal to 0.1155. That's where those negatives cancel. And what are our units? Well, remember, if these are in units of concentration change per mole, let's say that's molarity per second, then we would need something that cancels out the concentration of this particular species and balances those units. And since the rate is in molarity per second, or moles per liter per second, and the concentration on the other side of the reaction here for our rate expression is in moles per liter, those two things are good. They're preserved. What we need is just a per second term. So that means that this K is going to be in units of per second, and we want to be careful that we are only including the number of sig figs that we actually know. So a quick example from your book when it doesn't look linear, so that you know that it does not fit the first order rate equation. Exactly the same process. So I have a data set of time versus the concentration of some species here. We'll just call it A. I took the natural log of that species because I know that that's the form of the integrated rate law. I made the plot where I plotted time on the x-axis, natural log of A on the y-axis here. And what you can see is this curvature here, which means that that relationship between those two variables is nonlinear. That's further bolstered by the fact that the r-squared value, I mentioned 1, means the dots or the points fit the line perfectly. Anything less than that is imperfect. This is quite far from that, which means that these data, the data are real, but the data do not fit a first order rate equation, which would lead us to believe that this is not a first order reaction. We need to investigate other orders.